Okay, for the next section, we're going to be looking at 4.1. Oops. So 4.1 is all about linear approximations. So first of all, what we have is we're going to define the symbol delta f to equal f of a plus delta x minus f of a. And we're going to note that we had the definition of a derivative. So this is what we mean when we say delta f. We had that definition of a derivative, which was limit as h goes to 0, f of a plus h minus f of a, all that over h. We're going to reformulate that. Sorry, and this should be of an a. We're going to reformulate that, and we're going to let the h be replaced with delta x, and this should represent a similar amount. So h is delta x. And so we get this statement there. And we said if delta x is small, then we could drop the limit and say as long as the delta x we're talking about is small, we can kind of get an approximation just using this part of the thing. The way we stated it in the previous bit was delta h itself, like the h was small, we could use the approximation. Since we're replacing h's with delta x's, we're saying if delta x is small, then we can make this approximation. Well, using our notation up here, we'll recognize that this whole top statement here, that we could replace that and call that delta f. So what we get is f prime of a is about equal to delta f over delta x. We can multiply the delta x across and get f prime of a times delta x is about equal to delta f, which will get ourselves this equation. Delta f is about equal to f prime of a times delta x. So this is kind of the basis. We're going to use this formula. We need to put a little bit around it, but this is kind of where the next formula and the formula we're going to focus on for the next few examples comes from. It's basically starting from the formal definition of the derivative, replacing h with delta x, and then using a couple different definitions. So we're going to say linear approximation of delta f. So we say if f is differentiable at x equal a and delta x is small, then we get the following statement, and it's going to be our formula right here. Delta f is about equal to f prime of a times delta x. Okay, and then I guess they also note, they note where the delta f was equal to f of a plus delta x minus f of a. So what this kind of does, if we look at kind of what this approximation is doing, if suppose we had a function here, so let's say we got a graph and we got some curve going upwards or something, it's just some function f. And let's say here is a and here is a plus delta x. So the difference between these two right here is delta x. Well, a will go up, that'll hit the function, that gives us a corresponding y value over here of f of a. And then a plus delta x will go up, it'll hit the function further down, That'll come over and that'll correspond to a y value of f of a plus delta x. And the difference between these two, so if we kind of trace out to where we are, the difference between those two is delta f. So this is the delta f we're going to approximate. How the approximation goes is if we use the tangent line, so we use the tangent line at A, so pretend this is our tangent line at A. Well, we can go over here, delta x, and then the distance here would be f prime of A times delta x. That would be from here up to here. So we're kind of using this, let's see, choose a different color. We're using this little green line here to estimate the distance from here up to here. And you can see there's a little gap there, so it's not perfect. We can see the smaller delta x is, the smaller the gap there is. As delta x gets closer to delta A, the gap gets smaller, so this approximation is better the smaller delta x is, because the gap between where the function actually is and the tangent line, the gap between those two gets smaller. So the smaller the gap is, the better the approximation is. So that's kind of what we're doing. We're using this f prime of A delta x. We're using this little bar here to try to represent the overall change in f. So next couple examples, we'll kind of deal with this idea. So we say, all right, example 1, we want to use linear approximation. To estimate, we get 1 over 10.2 minus 1 over 10. And then they say, how accurate is it? Okay, so delta f, remember delta f is equal to f of a plus it's f of a plus delta x minus f of a. This right here is our delta f. So that's 1 over 10.2 minus 1 over 10. So what we want to do is we're going to say, all right, well, delta f is going to be approximated by f prime of a times delta x. So what we have to do is we have to look at this statement right here. We have to look at all this, everything that's right there, and based on that, we need to find what is f of x, what is a, and what is delta x. We can label all those, then we can find f prime, and we know what a to evaluate it at, and we know what delta x to multiply it by. So if we kind of think about f of a needs to be 1 over 10, and then f of a plus delta x is 10, we have 1 over 10.2. We're going to make 1 over x our function. We're going to say a is 10, and then since 10.2 is 0.2 units from 10, our delta x will be 0.2. So when we go to solve this and to get our estimate, we say, all right, here's f of x. I need to find f prime of x. F prime of x, we want to remember f of x, if it's 1 over x, it's the same as x to the negative 1. I'm just doing this so we can use the power rule to make it easier. That'll be negative x to the negative 2. So we got negative x to the negative 2 there. And we're going to say, all right, delta f is f prime of a times delta x. So this will be negative a is 10 to the negative second power. And then that's going to be multiplied by delta x, which is 0.2. And that will get us our approximation to delta f. So this won't be exact. It should be kind of close, though. and we get negative 0.002. This is our approximation. That is about equal to delta F. So then they say, all right, that's about equal to delta F. They say, how accurate is your estimate? So to figure out how accurate the estimate is, we're going to calculate the error. So the error in this situation is going to equal, it'll be the actual delta F value minus the F prime of A delta X, the approximation. So it'll be the actual value minus the approximation. So the actual value, when I type that in, we'll be putting in 1 over 10.2 minus 1 over 10. That's the actual delta F value. We'll subtract from it our approximation. And then that's all in absolute value. So let's see what that is. So we get 1 over 10.2 minus 1 over 10. And then all that minus a negative, which is plus 0.002. And we get basically, this right here is equal to 3.921. We'll round it to 6. And we'll say times 10 to the negative 5. So this is a pretty small number. And we'll say that's a pretty good approximation. So this is pretty accurate. So that is our error. Okay, so the next bit of stuff we're going to learn, there's some notation that we can represent. Instead of using delta F equals F prime of A, or sorry, not equals, is approximately F prime of A times delta X. We can rewrite the equation using what are called differentials. So instead of we can basically write out this statement here using differential. So we kind of use dy and dx instead of delta y in delta x. So we get basically use, for differentials, we'll use dx instead of delta x, and we can use dy instead of delta y or delta f, because both these tell y values. So we could say they give us the statement here that they tell us dy, the differential dy, is equal to f prime of a dx. So we have that statement there. And then they say we can approximate delta y. Delta y is approximately dy, the differential dy. Well, since the differential dy is equal to f prime of a dx, we can replace dy with that, and we'll get delta y is about equal to f prime of a dx. And if we look at this equation and we kind of compare it to the original equation we started with up here, we'll see that they're very similar. We use, instead of delta x, we use a dx, but it's basically the same information. So it's kind of two different notations that represent similar ideas. So we're going to use some stuff this time they want us to use our differential notation. So for this next example, this is example 2, they say how much larger is cube root of 8.1 than cube root of 8. And the book doesn't say that they want us to do an estimate, but they don't really say it in the way they have it set up. So we're going to put the little word out front here. We're going to say estimate, because if it says how much larger is that than that, then we can just type that in the calculator. But now that we kind of say we want an estimate of it, if we want to figure out how much bigger the cube root of 8.1 is than cube root of 8, we're really asking what is the cube root of 8.1 minus the cube root of 8. That's what it's asking us to find. And we'll say, hey, we could view that as a delta y. And then our differential notation, we could say that is approximately f prime of a times dx instead of delta x. So what we're going to do is we're going to basically look at this, and we're going to note that this right here is delta y. That is the actual delta y value. We're going to approximate it by this format here. But in order to calculate this, we need to know what is our function, what is a, and what is dx. Well, since we have cube root of 8.1 and cube root of 8, our function is going to be cube root. We have 8 out to 8.1, so a is going to be 8. And then from 8 to 8.1, that's 0.1, so dx is 0.1. And so now if f of x is the cube root of x, we need to figure out what f prime of x is so I can figure out what f prime of a is. So f prime of x will be 1/3 x to the negative 2/3. So we get, okay, delta y is approximately 1/3. It's not x anymore, we're going to use a. A is 8, so that would be 1/3 times 8 to the negative 2/3. And then we multiply that by dx, which is 0.1. So we'll just put that in our calculator and say, all right, what is 1/3 times 8 to the power of negative 2/3? All that times 0.1, which ends up giving us, we're going to approximate it, and we'll say it's about equal to 0.0083 is our approximation. So this right here is approximately how much bigger that is than that. Okay, so that one's not too bad. We're just kind of using our, we'll note just our, you can use the delta notation or the differential notation somewhat interchangeably, and that there is slight differences as to, you know, what they mean, but it's, you can kind of use them in these approximations in more or less the same way. All right, so for example 3, we're going to go through and do this. This is kind of a word problem style thing. So we get a thin metal cable has length 12. So it's 12 centimeters. When the temperature is 21 degrees Celsius. And we want to estimate the change in length when the temperature is 24 degrees Celsius. We assume they tell us the change in length with respect to temperature is equal to k times the length, where k is equal to 1.7 times 10 to the negative 5th. And they say that this is a coefficient of thermal expansion. And so basically what we're looking for here is we're looking for the change in length. So we'll use differentials for this one, and we'll say, okay, we want to find dl. So we're looking for dl, and I guess really what we're looking for the change in, we're looking for the change in length, so we're looking for change in length. The change in length, we're going to say we can estimate that by, this is change in length with respect to temperature. We're going to estimate that by dl dt, the change in length with respect to temperature, at the change in temperature. The thing is the change in length with respect to temperature, We're going to base this around the starting value at a temperature of 21 degrees Celsius. So we want dl dt at 21 degrees Celsius, and then we want to multiply that by the change in temperature. So to get dl dt, it's the temperature at 21 degrees Celsius, we have to use this formula. So this formula will be the thermal coefficient times the length at 21 degrees Celsius. The length is 12 centimeters at 21 degrees Celsius. So we'll say this is equal to the 1.7 times 10 to the negative 5 times our 12 centimeters. And then that's multiplied by dt. dt would go from 21 degrees up to 24 degrees. So that's a change of 3 in our temperature. So we'll put that all in our equation here. So we get 1.7 times 10 to the negative 5 times 12 times 3. And that says we get 6.12 times 10 to the negative 4. So that's 0.000612. And the length, this will be centimeters. So that's a pretty small change in temperature. Again, what we're doing, because this step's maybe a little confusing, the change in temperature was 3 units. They told us dl dt is K times L, so this right here is K times L. So this value here is the K. And, oops, sorry. That value there is K. This value here, since we're looking at the change in temperature at 21 degrees, this is the length at 21 degrees Celsius, which they told us in the problem statement was 12. And then we just use our approximation, which is, normally it's f prime of a, but instead we're using our Leibniz notation, so it's dl dt, and we're basing that around 21 degrees as our starting point. And then we have dt, which we could say is the change in temperature, and that's 3. And we use that to get our answer. So next group of problem here, we got something about approximating pizzas. Then we're going to look at this idea called linearization. And then we have one linearization idea. And then after that, we'll look at a little bit of percent error and error bound stuff. The percent error and error bound doesn't get tested on super heavily on the AP test. So from this section, the linearization and the linear approximation, those get tested on the AP test pretty frequently, but the errors on it get tested on less. So, okay, we're gonna look at this example, and then we'll get a little bit more and wrap it up. So we get the Bonzo Pizza Company. Let's see here. Claims its pizzas are circular with diameter 50 centimeters. Part A, what is the area of the pizza? Okay. And then part B, estimate quantity of pizza lost or gained if the diameter is off by at most 1.2 centimeters. Okay, part A for this should be pretty easy. Part A, pizza circle, so it's pi times radius squared. They gave us the diameter, so to get if we take the diameter and cut it in half, that's the radius. So it's pi times diameter divided by 2 squared, which this will equal pi times 50 divided by 2 squared. So basically it's pi times 25 squared. And we'll say that is about equal to Okay, pi times 25 squared is about equal to 1963.495, and that's the centimeters cubed, or centimeters squared, since it's area. Okay, so that's part A. That's not too bad. Part B, estimate the quantity of pizza lost or gained if the diameter is off by 1.2 centimeters. Okay, so we're trying to figure out the change in area. That's the amount of pizza we'd gain or lose. We can approximate that by area prime, and then delta x. Or I guess we'd say delta r, because r for radius. So if the area is pi r squared, if that's our area function. Wait. They're doing it in terms of diameter. So let's say, let's use capital D for diameter. So we're going to say D is for diameter. So instead of the radius is off by 0.12 centimeters, we're saying the diameter is off. So my area function is going to be pi times the diameter cut in half squared, which, let's simplify that a little bit. That'll be area. It'll be pi over 2 squared is 4. And we'll leave this as the diameter squared. So here's our area function in terms of diameter. So if I want to do area prime, that would be pi over 4. And then we would get basically 2 times the diameter. And this would equal pi over 2 times diameter. So we got pi over 2 times diameter is our A prime. So what we'll end up doing there is saying, okay, this is going to be about equal to pi over 2 times diameter. And this delta diameter is going to be, you're either over or you're under by 1.2. So we'll get, they said the diameter is 50, so we got basically pi over 2 times 50. And then we have plus or minus 1.2 for b multiplied to that for our estimate. So that's going to be about plus or minus, let's see, what, pi over 2 times 50, the diameter, times the 1.2 that we're off by. And I'm ending up getting about 94.248. That's area, so that would be cubic centimeters, square centimeters that we gain or lose. So basically, if you're over or under by 1.2 on the diameter, you're gaining or losing about 94.248 square centimeters of pizza. Okay, so that wraps that one up. And I think we're going to pause on this video here, and we'll do the last linearization and the last step in the next one.